Welcome back to another lecture. So in this lecture, we're going to try to predict whether a chemical reaction is going to move on or not without knowing the pKa. Okay, but we're going to remind ourselves that in a chemical reaction, if there is one side that is going to donate H+, it will create a conjugate base. A strong acid will create a weak conjugate base. So a weak conjugate base. And because it's a weak, it will be less reactive. Okay, less reactive, and that's a good news. Okay, we want it to be less, reactive. And if it's unstable, it means it's gonna go after another. It's gonna go after hydrogen. It will get hydrogen. It will go back to the starting compound, starting point. Okay, so acid is going to give up an H+, and it will generate a conjugate base. A conjugate base has 2 electrons. Okay, the question is it stable? How do I know whether that conjugate base is stable or not? Okay, and let's go after a couple of terms that we need to watch them. Okay, first thing is, where is the negative charge? Okay, so we're going to locate the negative charge and like in which atom is sitting. Second, are we dealing with resonance structures? Do we have any induction effect? And what's the induction effect? The induction effect is like, let's say we have electronegative elements. Maybe they are not directly attached to that negative charge. Couple of bonds, they are far, but still they can pull the electrons, and because they can pull the electrons, they will make the system less reactive, and that means it will be stable. And last thing is, okay, the orbitals that are involved. If we have like a sp hybridization versus sp3, sp is more electronegative than sp3. Okay, and that's gonna change the stabilization or stability of the negative charge. Okay, and if I go with abbreviation of each in like the first letter of each factor, let's say we're going to take A, R, I, and O. We will come with A, R, I, O, or RU, and I'm going to use this abbreviation from now to talk technically about whether that conjugate base is stable or not. Okay, the first thing that we're going to go after it will be the atom. So in this case, I have a butane, okay, reacted with a base. Okay, what do I have on this here? On this corner, I have a carbon atom. So if I take H+ from it, I will have a carbon with a negative charge. So this is a carbon with a negative charge. Okay. Well, if I do the same reaction with propanol, I will get a negative charge on oxygen. Okay, now let's compare them. Which one is more stable? One, it has negative charge on carbon. The second one on oxygen. Electronegativity, it says oxygen is more electronegative than carbon. What does it mean? If you are supposed to have a negative charge, it should be on oxygen. Okay, and oxygen is more capable of handling the negative charge than carbon. Carbon will not be happy because it has a negative charge. Well, oxygen got extra one, and because of electronegativity, it will be more stable. Than what? Than this one. Okay, more stable than that one. That means the propanol will be a stronger acid than butane. Okay, than the butane. Okay, I want to remind you a couple of things. So I'm going to talk about the acidity first, and I will come back again to the same reaction. Okay, so how do I figure whether one acid is stronger or weaker than the second one? Okay, we have acid, whenever we talk about acid, we have H attached to X. Okay, let's go with this. Our X is going to be a fluoride, let's say chloride, next bromine, and last one I go iodine. Okay, and in order to behave as an acid, we need technically to break this chemical bond, or we need to take the 2 electrons and give them to X. Okay, so we need to break that chemical bond. The question is how much energy we're going to spend. The less energy we spend, stronger acid will be. Okay, let's talk about also size of those bonds. Okay, size of any element to the right side of the periodic table decreases, down in any group it increases. Okay, what does it mean? It means this. It means this is fluorine, that's chlorine, bromine, and the last one it will be the iodine. Okay, that one is iodine. Okay, now let's put H. Okay, call this one, for example, H F bond. This is going to be HCl. This is going to be HBr, and that one is going to be HI. So this is HF. Okay. Why the bond is getting longer? Okay, because the size of the elements is getting bigger and bigger. So the bond it will be longer, okay, than the previous one because the radius of the element went up. So again, this is a fluorine, bromine, and iodine. Okay, which one it will be easier to break? Clearly, the one that has the longest bond. So breaking HI, it will be more favored, or it will be easier than HF. So based on bond, until now, HI is a stronger acid than HBr, and this one is stronger than HCl, and the last one is going to be stronger than HF. Okay, so strongest acid it will be HI, and the weakest acid it will be HF. Okay, now what will happen if you break those bonds? Okay, if you break them, those two electrons will be taken, and then they will be taken by the anion. Okay. When I say anion, I'm talking about the halogen element, fluorine, chlorine, bromine, or iodine. Okay, let's give them the electron. Okay, if we give them the electron, we're gonna get this. We're gonna get H plus and what? Fluoride. Okay, chloride, bromide, and this one is gonna be the iodide. Okay. So again, we have H in front of all of them. Okay. This is output of HX is turning to H plus, and what's the X here? Fluoride, chloride, bromide, iodide. Okay, remember, this time I put a negative charge on the top of them. Okay, what does it mean? It means each of them now has one extra electron. Okay, these elements are not neutral. Okay, these elements are not completely innocent. They do have a bunch of electrons, and new electron is gonna have some repulsion with them. Okay, new electron is not that really welcome unless it cannot sense those electrons, or maybe it's too far from them. Okay, too far from them. The one that has the biggest size, it can easily accommodate the extra electron. So we say iodide is more capable of handling the extra electron. And you use this term or keep this one in your mind. Okay, if ratio of charge to volume, okay, goes down, the ion will be more stable. Okay, in this case, the charge for all of them is -1. Only thing that is changing is the volume. Okay, as we go down in any group, volume or size is going up. So what does it mean? It means the denominator is going up. -1 divided by a bigger denominator, it will give you a smaller ratio. So iodide is more capable of handling the negative charge. That's one. Iodide has the longest bond. Breaking that bond, it will be easier. Okay, and because it's easier, it will cost us less energy. So two facts. One, I'm going to spend less energy to break the bond. Okay, I'm spending less energy to break it when it's a lengthy bond. That's one. And the second thing, when I break the bond, I get an ion. I get an ion that is more stable, more capable of handling the negative charge. Iodide is the best one. Okay, iodide is the best one. Now, when you are dealing with element that in the same group, okay, same period, in that case, go with electronegativity. Okay, electronegativity will be the most important thing. So here, when I'm, these two, if I take an electron H from them, I get HB plus, and what else? I get this. O -1 charge, and here I get carbon. Clearly, carbon has 2 more hydrogens, and we did not show them. This one is -1. Okay. Carbon belongs to the second period. Okay. Second period. And oxygen as well. Okay. So both carbon and oxygen belong to n equal to or to the second period. In this case, if you're dealing with elements that belong to the same period, go with electronegativity. The one that has higher electronegativity is more stable. Oh, it has higher electronegativity than carbon. That means this one is more stable. Means stronger acid. This one will be stronger acid. Okay, so I figured that this one is going to be a stronger acid than butane. Okay. Next, what will happen if we go down in one group? And let's write this example. We have CH3, okay, attached to oxygen. Then we have hydrogen. This is equal to technically this. Okay. And next example is CH3 attached to sulfur, and I go hydrogen. So you can draw it as sulfur and then hydrogen. Okay. Now, which one of this is a stronger acid? 1 or 2? Which one is a stronger acid? Stronger acid. Okay. This is a question. Okay, you need to answer it. So please think about it. Okay, and pause the video here and try to answer the question. Okay, great job. Okay, so now let's go after the answer. Okay, I have carbon, CH3, attached to O, H. If I reacted with a base, it will give me HB plus, and what do I get? CH3 attached to O, and O, it will have -1 charge technically. And how about this? CH3, O, so forgive me, H, S, and H here plus B, we get, okay, so let's go with this. Let's say we are dealing with equilibrium. We go HB, and then what else? CH3, and this is going to be a sulfur. And sulfur, it has 3 lone pairs. I can draw the same thing for it here. So let's say is CH3. This is oxygen. Okay, -1. Sulfur is -1. Remember, size of the element to the right side of the periodic table decreases. Down in any group, it increases. Okay, so sulfur has a bigger size than oxygen. So I'm going to say size of sulfur is bigger than size of oxygen. Okay, sulfur belong to n equal 3, third period. Oxygen belong to n2, the second period. What does it mean? It means this one is more capable of handling the negative charge. So this is going to be a stronger acid, and the pKa for it is around 10. Well, the pKa for the top one is around 16. It's not 16, it's around 15.17 actually. 15.17, and this one is 10.4. So this is stronger acid than CH3OH, or methanol technically. Okay, thank you very much. And next lecture, I'm going to cover other effects like resonance or inductions. Okay, I will see you very soon.